Welcome to today's physics class. Today, we are diving into a fascinating topic that simplified our understanding of electric fields and paved the way of modern tech like smartphones and satellites. Yes, I am talking about Gauss law and electric flux. Let's start with a quick story about the person behind this law, called Friedrich Gauss. He was a 19th century mathematical genius who, even as a young student, could solve complex problems with surprising ease. Okay, so he was a 19th century mathematical genius. Even as a young student, he could solve complex problem with surprising ease. His law fundamentally changed how we calculate electric field. Electric fields. Okay. Like Gauss, I hope your curiosity and problem solving skills will help you unlock the secrets of physics. Okay. Okay. So before um, get into the topic, to get our minds warmed up, let's do a quick three MCQ quiz to recall some of the important concepts from previous classes. Okay. So I will share the screen now. Okay. Right. First question. What is the unit of electric field? What is the unit of electric field? Newton per coulomb or joule or volt or ampere? Choose one. Which one is correct? What is the unit of electric field? Already you know that electric field. Yeah. So for every charge, there is a electric field. Yes. Option one. Yeah. kgPV. So beta. Yes. Good. Any other option? Any other students? Just recall your previous classes. Electrostatic charges, point charges concept. Yeah. Already you know that. Yes. Another one response. Yes. One. Okay. Good. MSM. Okay. Good. One. Very good. Super. Clear. KGBB Junior College. Yes. So we can choose Newton per coulomb. Okay. Let me see later. Okay. Yes. Newton per coulomb. Yeah. Newton per coulomb. Yes. Okay. Good. What does Coulomb's law describe? Already you know that Coulomb's law. Yeah. Coulomb's law. So Coulomb's law is how to say Coulomb's law describe about option two. Okay, option two. Option two. Force between charge is option two. Yes, yes, correct. Lot of very good responses. Very good. Two. Yes, very good. Yes. Yeah. Force between two charges. Yeah. Already we know that Newton's law of gravity. So which describe the force between masses. But Coulomb's law, it describe the force between the charges. Already we know that F is equal to K into Q1, Q2 by R square. Yeah. Okay, very good. Good. And the final one, what is the direction of electric field due to positive point charge? We have a two type of charge. One is positive, another one is negative. So here, and already you know that for every charge, there is a electric field around that charge. Yeah. So electric field is nothing but it is a like how to say when you place a test charge towards that source charge, that charge may be attractive or repulsive, depends upon the charge. Yeah. So we can draw the electric field lines, which is an imaginary line by which we can imagine how the electric field lines or how the electric field passing away or towards a charge depends upon the positive or negative. Yeah. So for the third question, option 2, option 3, away from charge. Okay, good. 3, 1. Okay. 3, 3, 3 parallel to the charge. Okay. Away from the charge. Okay. 1 towards the charge. Okay. 0. Okay. 2, 2. Okay. For positive point charge, electric field always directed from the charge. So away from the charge. But in terms of negative charge, the direction of electric field always towards the charge. Is it correct? Okay, good. So we can choose option 2 here. Okay, let me check what is the answer. Okay, submit, view score. Yes. For the first one question, what is the unit of electric field? Newton per coulomb. Very good. Good. What does the Coulomb's law describe? Yes. Force between the charges. And the final one, what is the direction of electric field due to a positive point charge? For direction of electric field, for the positive point charge, always away from the charge. In terms of negative point charge, it always towards the charge. Okay, right? Okay, good. Super. Great. Okay. So now let's introduce the main concept for today. First, electric flux. Okay. Electric flux. Think of electric flux as the measure of how many measure of how many electric field lines pass through the surface. This is a definition for electric flux. So electric flux is nothing but it is a measurement. Okay. Measure of how many electric field lines pass through the surface. Okay. For example, here you can see the one whiteboard. So this is one of the examples for any surface. Yeah. So here one charge is there, like in that space. Okay. So maybe it may be positive charge or negative charge. So for the positive charge, the point charge, positive point charge, electric field lines away from the charge. So electric field lines concept is there. So electric field lines passing through the surface like that. Yeah. Because electric field lines radiate from that positive charge and it passing through this surface. And then you can measure how many electric field lines passing through this surface. Then you will get electric flux. Okay. It is nothing but like a catching method like that. Okay. Okay. So there is a formula for electric flux. We can write this is pi. Okay. So pi is equal to E dot A cos theta. E dot A cos theta. So here E is the electric field strength. Yeah. E is the electric field strength. A is the surface area. And theta is the angle between electric field and surface normal. This is surface, this is normal. So angle between the electric field and the surface normal. Okay, so pi is equal to E dot A cos theta or EA cos theta. We can say that EA cos theta. Okay, right. So the unit for electric flux. So now you know that EA cos theta and the units Newton meter square by Coulomb. This is a unit for electric flux. Okay, right. Next, we have Gauss law. So Gauss law is a powerful tool. It is a powerful tool that relates total electric flux through any closed surface. Through any closed surface to the net charge enclosed within the surface. Within the surface. Okay. So Gauss law, it is a very simple and powerful tool that relates total electric flux through the any closed surface to the net charge enclosed within that surface. So, for example, you can take one closed surface and you have to find that how many charges inside the closed surface and how many charges outside the closed surface. So, for the surface outside the charge does not contribute any electric flux. So, we can neglect. Okay, we don't consider outside the charge. We have to only consider the charges within the closed surface. Then only we get electric flux. So in that case, we can use Gauss law. Okay, so Gauss law for total electric flux through the any closed surface to the net charge enclosed within that surface. So Gauss law formula again pi is equal to Q enclosed by epsilon naught. This is the formula for Gauss law. So here also you will find that electric flux for the closed surface. So Q enclosed means the charges enclosed within the surface. That's why we can write enclosed like that. Okay, right. So this is a total charge inside the surface. Inside the surface. Okay. And already you know that epsilon naught permittivity of free space. permittivity of free space. Is it correct? So already you know that it has a value. What is the value of epsilon naught? Anybody know? Please tell. What is the value of epsilon naught? Permittivity of the free space. It is constant value. Yeah. You can tell the value with the units also. Okay. Just tell the value only. What is the value of epsilon naught? Anybody? Permittivity of the free space. Epsilon naught. What is the value? Okay, no issue. Okay, I will write 8.85 into 10 power minus 12 into, so for unit Coulomb square by Newton meter square. This is the value and unit of the epsilon naught. We can write 8.854 like that. So we can just write like that 8.85. But 10 power minus 12 is very, very important. You don't write 10 power minus 12, sorry, minus 13 or plus 12 like that. So it is very long, very wrong. Okay. So you have to write exact 10 power minus 12. Okay. With the unit Coulomb square, Newton meter square. Okay. Right. So Gauss law is especially useful for calculating electric fields for symmetric charge contribution like spheres or cylinders. So here I will write the key steps to apply Gauss law. First of all, you have to identify the charge contribution, charge distribution. Okay. First of all, you have to identify the charge distribution. Charge distribution means, for example, it may be point charge or it may be line of charge like that. So Gauss law is especially useful for calculating electric fields for symmetric charge distribution like spheres or cylinder. So before applying Gauss law to find the electric field, you have to find the important four concepts. First of all, identify the charge distribution, or it may be point charge, or it may be line of charge. Then second, choose a symmetric Gaussian surface. Symmetric Gaussian surface. Okay. So what is the use of choose a symmetric Gaussian surface? Because it simplifies our calculation to find the electric field. Okay. So choose a symmetric Gaussian surface step, which is very crucial in our Gauss law method because it simplifies the calculation. For example, for a point charge, you can use sphere Gaussian surface. Okay. Note that very important line. For a point charge, you can choose a symmetric Gaussian surface sphere, that is spherical Gaussian surface. For a line of charge, you can choose the cylindrical surface. So I can write cylinder here. So this is a very exact, very ideal surface for that each type of charge distribution. For point charge, you can select cylinder or cube, but they are a low symmetric Gaussian surface. For a high symmetric or exact ideal symmetric type, for a fine charge, sphere. For a line charge, cylinder. Okay, you can change that, or you can exchange that surface, but it provides a low symmetric Gaussian surface. Okay, right. Third point. So first 2 point here. Okay, and third point, calculate the electric flux and the enclosed charge. Third point, calculate the electric flux and enclosed charge. You have to find the enclosed charge. Okay, right. And fourth point, last point, solve for the electric field. For the electric field. This is the important steps. Important 4 steps, key steps to apply Gauss law. Okay, you have to find the charge distribution, choose a symmetric Gaussian surface, and find the electric flux enclosed charge, and solve for the electric field. Okay, then only we can put that pi is equal to q enclosed by epsilon naught, and then for the electric flux, already we know that pi is equal to Ea cos theta. Yeah, okay, good. To visualize this, let's use a simulation. Okay, so this simulation will help you see how the number of field lines or flux changes. We move a charged object, and how the flux depends upon the enclosed charge, not the shape of the surface around it. Okay, like that. So I will share the screen now. One second. Okay. Yes. Okay. So here you can see that one animation. Before that, instruction. Select a charge type, Gaussian surface, adjust the charge magnitude and position. Watch how flux changes when charge crosses surface boundary. Try different surface shapes to see symmetry effects. Okay, right. Okay. So first of all, here you can see that one formula, Gauss law, pi E equal to Q enclosed by epsilon naught. Now choose point charge. Okay. You can see that one point charge is at center. Yeah. So red color line means electric field lines. It's radiate away from the charge. For the negative charge, you can see that blue color line. So it is towards the charge. Okay. Okay. So we can choose 5 nanocoulomb. For example, okay. 5 nanocoulomb. So charge at center, electric field lines passing away from the charge. Okay. We can choose the sphere Gaussian surface. Already I told you the sphere Gaussian surface is a well structured ideal Gaussian surface by the point charge. Okay. And we can choose surface size 2 units like that. You can change the units and you can see that. You can see that like the shape of that Gaussian surface enlarged or diminished. Okay, so we can choose 2 units. Okay, now the charge at the center. So position x position, y position 0, 0. Okay, x position, y position 0, 0. So it means it at origin. It is at origin. So 0, 0. Okay, right. So here you can see that electrical lines passing away from the charge, and that charge is at the center, that is 0, 0, and we can choose the sphere. Then now here, note it down, enclosed charge 5 nanocoulomb. Yeah, because we choose that 5 nanocoulomb. Okay, and we can change that charge. Electric flux 5.565 e power plus 2 Newton meter square coulomb. Electric flux, because already we have a enclosed charge. Then electric field. Okay, so electric flux you can calculate. Okay, and here you can see that important point, that is high symmetry. Calculation is simple. That's why we can choose Gauss law. We can select Gaussian surface to exact match with that charge type. Okay. So here you can see the high symmetry calculation is very, very small. For example, now I can move the charge outside the sphere. You can see that now. I can move the charge outside the sphere. Like that. Okay. So then you can see here, what is that? Only 0, because there is no charge enclosed within the surface. So there is no charge enclosed within the surface, means there is no electric flux. So 0 electric flux. Is it clear? Okay. Okay, right. So here you can see that the lines passing are around that sphere. That means in our space, a point charge, that we can say that a positive point charge, electrical lines radiate away from the charge. Yeah. So the electrical lines passing through the surface like that and exit from the surface. But charge is that is at here. Yeah. But electrical lines passing through the surface and exit from the surface. So cancel out each other. That's why we can see that electrical lines around that circle like that. But charge outside the sphere. So there is no electric flux. That's why we can write 0. Okay. So now you may encounter with one doubt. That is, sir, what is the like for example, positive charge? You can say that's point charge. You can say that's a ideal Gaussian surface, a sphere. Suppose if we choose another Gaussian surface, for example, okay, before that, I will move into the charge at the center. Okay, like that. Okay, right? Okay. So the same positive charge, but now I can choose different Gaussian surface. For example, cylinder. Here you can see that cylinder. Yeah. Now, please look at that here. Low symmetry. Calculation is complex. Then what is the use of our electric field line calculation? Because calculation is very complex. Yeah. then only we need the Gauss law. So low symmetry calculus is complex. So what is the ideal Gaussian surface for the point charge? It is a sphere. Okay, sir. And cylinder Gaussian surface is ideal for which type of charge configuration? You can say that. For that, we can choose point charge into line of charge. So here I am choosing line of charge. In that case, now you can see that high symmetry calculation simple. Enclosed 5 nanocoulomb electric flux as usual 5.65 like that. Yeah. Okay. And third charge configuration, for example, here you can see that plane of charge. Okay, plane of charge. So plane of charge, here you can say that you can see low symmetry calculus is very complex. So in that case, for a plane of charge, we can choose cube. Okay, we can choose cube. So for a plane of charge cube, and then you have to uh, move the charge to find the high symmetry position, because like that. Once again, we can choose. So we have to find exact one point anywhere around that surface. Okay. Sorry. Okay. Okay. Right. So for a cube, for a point of charge, we have to choose sphere. Before that, we have to move the charge into zero position. Yes. Okay. Correct. So high symmetry calculation symbol. For a line of charge, you can choose a cylinder. For a plane of charge, you can choose a cube, and then you have to move the charge according to that high symmetry position. Then only calculation is very simple. Okay, so this is a simulation for Gauss law. Okay, right. So let's apply Gauss law to solve some problems. We will work through two examples on the board. First of all, problem number 1. Problem number 1. A point charge of 5 microcoulomb is enclosed by a spherical surface of radius 0.3 meter. Calculate the electric flux through the surface. Okay. A point charge of 5 microcoulomb is enclosed by a spherical surface. Already we know that for a point charge, ideal Gaussian surface is spherical surface. So spherical surface of radius 0.3 meter. Calculate the electric flux through the surface. Okay, right. So here Q is 5 micro coulomb. Micro means 10 power minus 6. Okay, so 5 into 10 power minus 6 coulomb. And radius 0.3 meter. Yeah, so these are the data given. So concept, according to the Gauss law, the total electric flux through a closed surface depends only on the enclosed charge. Depends only on the enclosed charge, not the size or the shape of the surface. Okay. So the electric flux through the closed surface depends only on the enclosed charge within the surface, not the size or shape of the surface. Okay. So formula, already we know that formula Q 5 into 10 power minus 6 coulomb, radius 0.3 meter, electric flux pi is equal to Q enclosed by epsilon naught, Q enclosed. So this is a Q enclosed. So 5 into 10 power minus 6 coulomb divided by, already I told you, the value of epsilon naught 8.85 into 10 power minus 12 coulomb square, Newton meter square. Okay. So we will get approximately 5.65 into 10 power 5 Newton meter square coulomb. Okay. For the 5 microcoulomb, we can get 5.65 into 10 power 5 electric flux. Clear? So this is a problem number 1. Okay. So then next problem number 2. So note it down. Okay. Okay. Good. Second problem number 2. An infinite line charge has a linear charge density of 4 nano coulomb by meter. Find the electric field at a distance of 0.2 meter using Gauss law. An infinite line charge has a linear charge density. So linear charge density denoted by lambda. Okay. So 4 nano coulomb per meter. Find the electric field at a distance of 0.2 meter using Gauss law. Okay. Right. For this sum, the data is given. First of all, linear charge density lambda is 4 nano coulomb per meter. So already you know that nano is 10 power minus 9. So coulomb per meter. Distance or 0.2 meter. And then we have to find the electric field. Yeah. So for a infinite line charge, electric field is radial and uniform. Okay. For a infinite line charge, the electric field is radial and uniform. For a line charge, already I told you, for a line charge, we will choose the cylindrical Gaussian surface because this is a ideal Gaussian surface for that line charge. Yeah. So we can choose a cylindrical Gaussian surface. Already we know that Gauss law is pi is equal to integral of EA, sorry, E dot dA or EA cos theta, which is equal to Q enclosed by epsilon naught. So here we will choose the cylindrical Gaussian surface. For our cylindrical Gaussian surface, it has a radius. Yes, while cylindrical surface has radius R and length L. Flux only passes through the curved side. Okay, so this is a curved side. So the flux only passes through the curved sides because at the top and bottom the angle is 90 degree. So cos 90 is 0. So we can say that flux is 0 at the top and bottom. So the flux only passes through the curved side. So the curved surface area for the cylindrical surface, already you know that for the curved CSA, curved surface area is 2 pi r L. Yeah. For our cylindrical surface of radius r and length L, the flux only passes through the curved side. Then we can put that curved surface area, that is 2 pi r into L. Yes, 2 pi into radius into length. So this is the area, that is curved surface area for the cylinder surface. For the flux formula, we have to multiply electric field with area. So that's why E dot 2 pi r L is there. Okay. Then we can move into that lambda. Okay. Please note it down. Okay, right. So we have pi is equal to E dot 2 pi r L. Okay. Pi means Q enclosed by epsilon naught. Yes, Q enclosed by epsilon naught equal to E dot 2 pi r L. Okay. We got to find E. So E is equal to Q enclosed by epsilon naught into 2 pi r into L. Is it correct? Okay, 2 pi r L goes here. So E is equal to Q enclosed by epsilon naught into 2 pi r L. But we don't have a enclosed charge here. We only have the charge density. Yes. So enclosed charge, Q enclosed equal to charge density into L. This is a formula for which is related to the enclosed charge and charge density. Q enclosed equal to lambda into L. We don't have a Q enclosed here, but we have a only charge density, linear charge density. So lambda only is there. Yeah, and L is there. Okay, right. So here Q enclosed, we can replace in terms of lambda into L. Okay. lambda into L here. And we can cancel out the L. So E is equal to lambda by 2 pi R epsilon naught. So lambda is equal to, sorry, E is equal to lambda by 2 epsilon naught into R. Now substitute the values. Lambda 4 into 10 power minus 9 coulomb per meter, 2 pi epsilon naught 8.85 into 10 power minus 12 coulomb square Newton meter square, radius 0.2 meter. Yeah. So we can calculate. So we will get the approximately 3.6 into 10 power 2 Newton per coulomb. So this is a value, final value. Please note it down. So here electric field at a distance of 0.2 meter is 3.6 into 10 power square, 10 power 2 Newton per coulomb. So a great real life example of Gauss law is a car during a lightning strike. The law explains why no electric field exists inside the charged conductor. Okay, the law explains why no electric field exists inside a charged conductor. The charge distributes on the outer surface and the field inside is zero, keeping that occupant safe. Okay. So during lightning strike, we have to sit in that inside the car or bus because according to the Gauss law, it explains why no electric field exists inside the charged conductor because the charge distributes on the outer surface, outer the car, outer the bus. There is no field inside the charged conductor. That is the field inside the zero. So inside is safe. Okay, during the lightning strike. So keeping the occupants safe. Okay, clear? Now it is your turn to apply what you have learned. Okay. So now I will share the screen. So this quiz has five questions based on today's lesson. I will share the screen now. Yes, Faraday butterfly net. Yes. So Faraday gauge is another one example based on the Gauss law. Yes, very good, super. Okay, yes. First question: what is electric flux? What is electric flux? Charge density, electric field strength, field lines through the surface, or voltage? Option 3, option B, 3. Okay, okay, good, good. Okay, 3, C, C, B. Which one is correct? Which one is correct? B or C? B, C. Okay, Yes. So electric flux is a measurement of how the electric lines passing through that surface. Yes. Yes. C. Okay. We can choose C. Correct. Okay. Second question. What is the formula for Gauss law? What is the formula of Gauss law? Option 2, 1, 2B, 2B. Yes, very good. Yes, B. Very good. Pi is equal to Q enclosed by epsilon naught. Okay, so enclosed is a subscript, so that's why I am putting underscore. So Q enclosed by epsilon naught. Yes, very good. Super. And the third question, when is the electric flux through the closed surface zero? Very important question. B. Susma Krishnaveni, B. Vallu, B2, Mageshwari 2, Nillimarla, B. Okay, option 1, GJC 1, Mageshwari 2, APRG, KGBP, IFP, okay, B, A, OPPO, okay, okay, 2 or 1. Which one is correct? So some of the students choose the option 1 and some of the students choose the option 2. 2, okay. So when is the electric flux through the closed surface zero? Uniform will, okay, okay. Let me check. What type of symmetry is best for applying Gauss law to a point charge? For a point charge, we have to apply that type of symmetry to make the calculation is very simple and to see the high symmetry. Yeah, because we can encounter the low symmetry also. Yes. Okay, option B, 2, 2, 2. Yes, 2, 2. Yes, correct. Great. So what type of symmetry is the best for applying Gauss law to point charge? Already I told you, spherical. In terms of line charge, you have to choose cylindrical. Okay. In terms of planar charge, you have to choose cube like that. Okay, right. So for a point charge, spherical is the ideal Gaussian surface. Clear? Okay. Now, final question. What is the electric field inside the charged conductor? 2, 1, 1, 0, A, 0, 1, super, Irlam, ABRG. Very good. Okay. A. Yes, yes, correct. So, electric field inside the charged conductor, 0. Already I told you during lightning strike, we have to move, we have to sit in that inside the car or inside the bus. So Faraday gauge is also another example. Yes. So one told that. Okay, very good. So now check, but for the third question, okay, right. What is the electric flux? Yes, field lines passing through the surface. What is the formula of Gauss law? Q enclosed by epsilon naught. Yes. And the third one. When is the electric flux through the closed surface? 0. So many of the students told that uniform field. That is option B. No, it is wrong. No charge inside. Yes. So electric flux for the Gauss law, we have to choose a closed surface. In that closed surface means so that surface should enclose a charge. Then only we can find the electric flux. Suppose there is no charge inside the surface, inside the closed surface. There is no. That means there is no enclosed charge within the surface. Then electric flux is 0. Yeah. So Option A is correct. No charge inside. Okay, right. And fourth one, what type of symmetry is best for applying Gauss law to a point charge? Already many of the students choose option B. Yes, correct. Spherical. And the final one, what is the electric field inside the charged conductor? Zero. Very good. Super. Correct. So excellent. Now let's hear from some of you. I got like a few volunteers to explain one of the concept we covered today, either electric flux or Gauss law, in your own words. Okay, don't be shy. So this helps solidify your understanding. Also, feel free to ask any questions or share other real world example. For example, one student told that Faraday gauge. Yeah. So now, like how to say how lightning rods work. I am here to address any doubts you have, and I can use the whiteboard for sketches if needed. Okay. Any doubt, or you can say that a definition for electric flux or Gauss law in your own words. Okay. So to wrap up, let's quickly summarize the key points. First of all, electric flux. Electric flux measures how the flow of electric field through the surface or electric field lines through the surface given by the formula pi is equal to EA cos theta. Yes. Then second one, Gauss law. Gauss law. It says that total electric flux through the closed surface is directly proportional to the enclosed charge. That is pi is equals to Q enclosed by epsilon naught. Gauss law is a powerful tool for calculating electric fields, especially for systems with high degrees of symmetry. Okay. The total flux depends only on the enclosed charge, not the shape or size of the surface. Okay. Right. For homework, for homework, okay. Hmm. Okay, sir. Once again, please note the homework now. I will share the screen. This is your homework. Please complete these two problems. First problem, a charge of 3 microcoulomb is at the center of the cube at the side length of 0.5 meter. Calculate the electric flux through the one face of the cube. Second one, research and write short paragraph, 100 words on how Gauss law is used in designing the capacitor for electronic devices. So this is your homework. Please complete. Okay. So thank you, students. Thank you, teachers. Jai Hind, Jai Bharat, Jai Vidyasati. Thank you, sir.